Today is the final lecture of week 2, and we will continue our discussion of solving second-order differential equations and second-order circuits. Recall that we had already reviewed the various types of responses for second-order differential equations, including overdamped and critically damped, underdamped and undamped, and the characteristics of these types of responses, including settling time, fastest response, overshoot, etc. Since we will continue the discussion, let's go ahead and jump right into some examples.
Assume that the following system is initially at rest. Y of 0 equals y dot of 0 equals 0, and the input is a constant step x of t equals a u of t. What is the complete solution y of t for t greater than or equal to 0? The system is the second derivative of y plus 2 times the first derivative of y plus 5y of t equals 10x of t. Remember that our governing standard differential equation is the second derivative of y plus 2 zeta omega sub n dy dt plus omega n squared y of t equals k omega n squared x of t. So the first thing I'm going to do is compare coefficients in order to identify k, zeta, and omega sub n. So 2 zeta omega sub n is equal to 2, omega n squared is equal to 5, and k omega n squared is equal to 10. So from here we know that omega n is equal to the square root of 5 radians per second. K is equal to 2. And 2 zeta omega sub n is equal to 2. So zeta is equal to 2 over the square root of 5. Since zeta is less than 1, we have an underdamped response. Remember, the other way to identify the type of response is to find the roots of the characteristic polynomial. The characteristic polynomial is r squared plus 2r plus 5 equals 0. We can use the quadratic formula to solve for r. So r is equal to negative 2 plus or minus the square root of 4 minus 20 over 2. So r is equal to negative 1 plus or minus j2. Remember, when we have complex conjugate roots of the characteristic polynomial, that also indicates that we have an underdamped response. And we can compare this to the general form, which is negative sigma plus or minus j omega d, where d is the damping frequency and sigma is the damping factor. The general form for the underdamped response is y of t is equal to ka plus ce to the negative sigma t sine of omega dt plus theta. So now let's substitute in the values we already know. We know that k is equal to 2, so we have 2a plus ce. We know that sigma is equal to 1, so we have negative t. And we know that omega d is equal to 2 as well, so that's the sine of 2t plus theta. Now we have to use initial conditions in order to find a and c. Y of 0 is equal to 2a plus c sine of theta, and that equals 0. The first derivative of y of t is equal to negative c e to the minus t sine of 2t plus theta. This is using the product rule, so then we have plus 2c e to the minus t cosine of 2t plus theta. So y dot of 0 would be equal to negative c sine of theta plus 2c cosine of theta, and we set that equal to 0. We can rearrange this last equation and rewrite it as the sine of theta over the cosine of theta, which is equal to the tangent of theta, and that equals 2. So by taking the arctangent of both sides of the equation, we get that theta is equal to 63.43 degrees. And now we substitute this into the first equation. 2a plus c times the sine of 63.43 degrees, and that equals 0. And we solve for C, and C is equal to negative 2.236a. And finally, we can write the final answer. Y of t is equal to 2a minus 2.236a, e to the minus t, the sine of 2t plus 63.43 degrees. And you multiply by u of t to indicate that this is the answer for t greater than or equal to 0. All right, now let's try an example that involves a second-order circuit that can be described by a second-order differential equation. For the following circuit, the switch has been up for a long time and moves down at t equals 0. Find the output voltage V of t for t greater than or equal to 0. This is like a step response circuit where it switches from the 8-volt to the 12-volt source. So in this case, the input is the 12-volt source, and the output is V of t, the voltage across the capacitor. So unlike the problems before, we don't have the initial conditions. So we analyze the circuit at t equals 0 minus in order to find the initial conditions. So t equals 0 minus, the switch is up. We have DC conditions, and we want to find V of 0 minus and find I of 0 minus. So if I redraw this circuit at t equals 0 minus, I have the 8-volt source, the 5-ohm resistor, I have the capacitor modeled as an open circuit because I have DC conditions, and I have the inductor modeled as a short circuit because I have DC conditions. So here I have I of 0 minus, and here I have V of 0 minus. So I know that the initial current through the inductor, because I have an open circuit, is 0 amps. And because I have the open circuit, the initial voltage across the capacitor is actually the same as the voltage source. So that's 8 volts. So now let's analyze the circuit at t equals 0 plus. At t equals 0 plus, the switch has moved from the 8-volt to the 12-volt source. So the input is now x of t equals 12 u of t, where a is equal to 12. And remember that voltage across the capacitor is continuous for all time. So V of 0 plus is 8 volts. And current through an inductor is continuous for all time. So I of 0 plus is equal to 0 amps. And we're now going to analyze this new circuit in order to find the second order differential equation, which we're going to use to solve for V of t. So I have the 12-volt source, the 5-ohm resistor, the 1/5 farad capacitor, and the 1 Henry inductor. And then I define the current around this loop as I of t. And we're going to write the KVL equation. The KVL equation is the sum of the voltages around the loop is equal to 0. So I'm going to have 5 I of t plus V of t plus L d I of t dt, but L is a 1, so that's d I of t dt equals x of t. And we know that the current through the capacitor is C dV of t dt, so that's 1/5 dV of t dt. So now I'm going to substitute equation 2 into equation 1. So that equation becomes the first derivative of the voltage, dV of t dt, plus V of t, plus 1/5 times the second derivative of the voltage is equal to x of t. So now we're going to do a little bit of rearranging, and we have that the second derivative of the voltage plus 5 dV of t dt plus 5 V of t equals 5x of t. Now we can compare this to our standard governing differential equation in order to find k, zeta, and omega n. And we get that omega n is equal to the square root of 5. K is equal to 1, and 2 zeta omega sub n is equal to 5. So zeta is equal to 5 over 2 on the square root of 5, or the square root of 5 over 2. In this case, zeta is greater than 1, so we have an overdamped response. Next, we solve the characteristic polynomial for the roots, and we have r squared plus 5r plus 5 equals 0. And the roots are r is equal to negative 1.38 and r is equal to negative 3.62. We have two real distinct roots, so once again that tells us this is an overdamped response. And the form of the overdamped response is v of t is equal to Ka, which is 12, plus C1 e to the negative 1.38t plus C2 e to the negative 3.62t. And recall that the way that we find C1 and C2 is by using the initial conditions. So the first condition is V of 0. V of 0 is 12 plus C1 plus C2 is equal to 8. So that equation simplifies to C1 plus C2 equals 4. Next, we have to use the initial condition for the current in order to find the second equation in order to solve for C1 and C2. So I of t, which is the current through the capacitor and the inductor, is 1/5 dV of t dt, which means that's 1/5 times the derivative of the voltage, or negative 1.38 C1 e to the negative 1.38 t, minus 3.62 C2 e to the negative 3.62 t. And then we evaluate that at t equals 0. So I of 0 is equal to negative 0.276 C1 minus 0.274 C2, and that equals 0. So now we have two equations and two unknown. So when we solve those, we get that C1 is equal to 2.469 and C2 is equal to negative 6.469. And finally, the answer for V of t. V of t is equal to 12 minus 6.469 e to the negative 1.38 t plus 2.469 e to the negative 3.62 t. And we multiply that entire equation by u of t. Let's do the final example for today's lecture. For the following circuit, the switch has been open for a long time and closes at t equals 0. Find the output current I of t for t greater than or equal to 0. Remember that the standard governing differential equation is the second derivative of y plus 2 zeta omega sub n plus dy dt plus omega sub n squared y of t equals k omega n squared x of t. As before, the first thing we're going to do is find the initial conditions. So we draw the circuit at t equals 0 minus when the switch is up under DC conditions. And we use this to find I of 0 minus, the current through the inductor, which is continuous for all time, and to find V of 0 minus, the voltage across the capacitor, which is continuous for all time. So when I redraw the circuit, I have the 3 amp current source, the 5 ohm resistor, the 10 ohm resistor, and the inductor modeled as a short circuit because we have DC conditions, and the capacitor modeled as an open circuit because we have DC conditions. So now I'm going to find V of 0 minus, which is the voltage across a short circuit. So V of 0 minus is equal to 0 volts. And I find I of 0 minus, And I can use the current divider because this is the same as the voltage across the 10 ohm resistor. So it's 5 over 15 times 3, which is equal to 1 amp. Now let's analyze the circuit at t equals 0 plus in order to derive the second order differential equation. So now the switch is closed, which means we've shorted out the 10 ohm resistor and we have a parallel RLC circuit. And remember, since voltage is continuous, V of 0 plus is still 0 volts and I of 0 plus is still 1 amp. So I have the 3 amp current source in parallel with the 5 ohm resistor, in parallel with the 1 Henry inductor, and in parallel with the 10 millifarad capacitor. Since it's a single node pair circuit and mostly parallel, I am going to use KCL to solve it. And my input is going to be the step function 3u of t because I have a 3 amp current source, so A is equal to 3. I have labeled the ground, the I of t and the V of t on this circuit, and I am now ready to write the KCL equation. The current through the resistor is V of t over 5, plus the current through the inductor, I of t, plus the current through the capacitor, 10 milli, dV of t dt, and this equals the input, which is x of t. This will be my first equation. The second equation will be a relationship between I of t and V of t. The voltage across the inductor, V of t, is equal to L di of t dt, but L is a 1, so it's going to be d I of t dt. Next, we're going to substitute equation 2 into equation 1, and this yields 1/5 di of t dt plus I of t plus 10 milli, the second derivative of I of t, which equals x of t. Now we'll rearrange this equation by using algebra and get the second derivative of the current with respect to time, plus 20 di of t dt, plus 100 I of t equals 100 x of t. So we equate coefficients to solve for omega n equal to 10 radians per second. The static gain k is equal to 1, and 2 zeta omega sub n is equal to 20. Therefore, zeta is equal to 1. Zeta equal to 1 indicates that we have a critically damped response. Polynomial r squared plus 20r plus 100 equals 0, and we get that we have repeated real roots of -10, which also indicates that we have a critically damped response. The form for a critically damped response is I of t is equal to Ka, where k is equal to 1 and a is equal to 3, C1 e to the -10t plus C2t e to the -10t. Recall we have to use initial conditions in order to find C1 and C2. So I of 0 is equal to 3 plus C1, which equals 1, and C1 is equal to -2. Now we use the initial voltage in order to find C2, and V of t is equal to L di dt. So it's going to be 1 times the derivative of I of t, where the derivative of it is -10c1 e to the -10t minus 10c2 t e to the -10t plus c2 e to the -10t. V of 0 is equal to -10c1 plus c2, and we set that equal to 0. We know that C1 is equal to -2, so C2 is equal to negative 20. And finally, the answer for I of t. I of t is equal to 3 minus 2 e to the negative 10t minus 20t e to the negative 10t. And this is for t greater than or equal to 0, so we multiply it by u of t. And this concludes today's lecture on solving second order circuits.